clear my screen and go back to current slide. Okay. I could have done that a different way, but I didn't, and I should turn on the projector light. All right, now, I think based on what happened in my last class, where we started with 2 people, and then as time went on, the class filled up. Announcements I made at the beginning, I needed to make again at the end as the people came in. So what I'll do now is wait, and before anyone has to leave today, let me know and we'll go over how we're going to end up things. If you have questions now, I'll talk about them now, but we'll just wait and hold those at the end and talk about how we're going to wrap things up. Is that okay? All right. And let's see if anything else. I'll try to remember to get all the issues covered. Let me see this one thing. The first test, have I returned that to you? Okay, everybody got it? Okay. Test 2, I'm still missing a few copies. And test 3, I think they just have started coming in, so I don't have any of those graded yet. But that's the other issue. With all this stuff been occupying just about every spare minute that I had, I'm behind in grading, okay? And after today, in fact, even before the day's over, I have 30 minutes of office hours between 5:30 and 6 this evening. I'm going to be grading like crazy during those office hours. I'm taking it home with me and grade there. And then tomorrow I hopefully have 4 hours in the office, because this thing will be over with. I'm not going to mess with anything else to do with it, I hope anyway, until after the term is over. And let me think. So I hope I'll be able to get just about everything graded between this afternoon, this evening, and tomorrow afternoon and tomorrow evening. Hopefully I'll have everything graded. It's a lot of grading to do, but I'm hoping to get that done and then hopefully get some other stuff back to you. So I'll talk about the rest of that before the end of the class. So let me know if anyone has to leave. I'll stop it and do that before you go. Okay. Last time we started in chapter 4, which was vector spaces. In 4.1, we started talking about vectors in the plane. And I believe we were down to example 1. Is that right? Before we ended last time?
Yes.
Okay. Now, I think I am going to change my slide here. Let's do example 1. To represent the vector u, and let me get my pen set up. Yuck. There we go. Here's vector u. Now, again, it's bizarre, but yesterday in my Calculus 2 class, we started talking about vectors. That book's written by the same author as this one, and I already told you my pre-calculus class written by the same text, same author as this one, and everywhere in both of the other texts, he uses the vector notation of angle brackets. In this text, he does not. So I'm going to try to be consistent with the text, but if I put a angle bracket in there, understand that's what it means. But this is a vector u, and since it is a vector, you have to understand from that means these are components of the vector, 2, 3. They look like they're coordinates of a point. They may or may not be, but they are, because this is a vector, components of a vector. It says to represent u, draw a directed line segment from the origin to the point 2, 3. Well, the point 2, 3 is 2 to the right, 3 up. Okay? Now this is the point 2, 3, coordinates of the point. Here is the vector u, and the vector u has components 2, 3. They look just alike, but they mean different things. This is a point. 2 for x, 3 for y. This is a vector whose horizontal component is 2 units to the right and whose vertical components are 2 units up. We could have drawn the same vector over here, okay? Here, okay? And that would have still been 2, 3. But it wouldn't have been either starting or ending at 2, 3. So understand the top one's a point, coordinates of a point, the bottoms are components of the vector. I wish they used angle brackets, and that would make it unnecessary for me to say all this. Now, to represent vector v, which is negative 1, 2, how would I draw it? Negative 1, 2. This time go to the left 1 and up 2. And there would be vector v. And this would be negative 1, 2. And there, since that's a vector, those are components of the vector. Okay? Pretty simple, pretty straightforward. Any questions? Okay? Now forgive me if I get sort of wacko here. I was starting to say we did vector addition, but that was in my other class, so sorry. Covering the same material in 2 classes but on different schedule is okay. One vector operation is vector addition, and what I'm going to do is delete this stuff so I can show it better here. To add 2 vectors in the plane, add their corresponding components. You know, I sort of wish I'd left that up there. I think I will. Let's go back. And this was vector u, which is, what was it? 2, 3. And here was vector v, negative 1, 2. Did it. Sorry. Okay. That's vector v. I can't help myself sometimes. I put all the angle brackets in there. Okay. Let's add those 2 vectors together. Okay? Well, as I just said, to add 2 vectors, u plus v, which means you take the vector u, I just did it again, 2, 3, and add to it the vector v, which is negative 1, 2. And how do you add vectors? You add the corresponding components. What will that be? 2 plus a negative 1 is 1, and I put an angle bracket again. 3 plus 2 is 5. Okay, I'll try not to do that. Okay, so we think it's going to be at 1, 5, which would be 1 and up 1, 2, 3, 4, 5, right there. Well, let's see what we just did. Okay, this we say is a sum u plus v, and we claim that is 1, 5. Okay, now notice here, if we had started with u and added the vector v to it, in other words, put the tip of v, the tail of v on the tip of u, and drawn it minus 1, 2, we'd have gotten right here. Or, and this is also vector v, which is also not by coordinates but by components, negative 1, 2. We could have drawn v first and then added u to it, which was up 2, no, right 2, 1, 2, and up 3, and sure enough, we get there. And this is vector u, which is, by components, 2, 3. Right 2, up 3. Well, guess what we've just drawn here? A parallelogram. Okay? And a parallel, they sometimes call this vector addition by the parallelogram method. If you're graphing it, it's not precise, it's kind of ugly, but that's how you do it. The easy way to do it is how we did it the first time. Add the x components, add the y components. You got it. Nailed it without having to draw any vectors, any lines, orienting tip to tail, tail to tip, or anything else, and you've got it locked. So the easy way to add vectors is by components. If you only have the graphical representation, then do it graphically. But the easy way is by components. Okay? Now, they also say in the next example, and by the way, generically, here's how you say this. Vector u plus vector v would be generically u1 plus v1, comma, u2 plus v2. And those are the components of the sum vector. Okay, and it says in the next example, one of the vectors you will add is the 0 vector, which is 0, 0. Now, did we talk about that last time? We represent the 0 vector by the number 0, but with a bar over it. In the book, they make it a bold 0. Okay, and its components are 0, 0. Did we talk about this at all last time? See, again, I'm going to be asking this all day because I can't remember which class I taught with about. In yesterday's class, I did. So obviously, in our class, we didn't. What is a little, I call it a major problem with the 0 vector? There's actually two of them. What did we say a vector was? A what? Say one more time. One more time. Okay, exactly. The two characteristics of a vector has a magnitude and direction. The title we gave, a directed line segment. A line segment has a magnitude, and the direction is its direction. So it has magnitude and direction. What's the problem with the 0 vector? What? Two problems with the 0 vector. It doesn't have a magnitude. Its magnitude is 0. And what's even worse? It doesn't have a direction. How can a vector point anywhere? It has no magnitude. There is no line segment there. So it has no direction. So in many ways, it's not even a vector, but we have to have it for completeness sake. So it is a vector. So, do you want to do these graphically? Well, we can. The book does, so let's do it. Let's clear this, and let's add two vectors. Here's a vector u is 1, 4. And here's a vector v, and it's 2, negative 2. Okay? Find the sum of those two vectors. What would be u plus v? The easy way to do it is what? And what do you get? 3, 2. Done. Okay? So stinking easy to add it component-wise. Okay? I'm going to do the B in a different color, if that's okay. Pick me a color. Purple. All right. Royal color. This is a different U. That's why I chose a different color. Is equal to 3, negative 2. And this new V is going to be negative 3, 2. Okay? And what is U plus V in this case? The good old 0 vector. And you see why we have to have it. If there was no 0 vector, some vector additions you couldn't do. Well, you need to do them all. So this is why we need a 0 vector. Okay? And the C one, what color you want C to be? Red. Okay. Here the U is 2, 1. And the V is our good old 0 vector, 0, 0. And what's U plus V in this case? It's going to be simply 2, 1. So basically, here's something we can say as a generality that, by the way, how are U and V related here? Just looking at that, how do they seem to be related? They're the opposite of each other. If you do a negative sign in front of here, you get negative 3 plus 2, which is what V is. So put a negative sign in front of here, and you get 3, negative 2, which is what U is. So these are the opposite vectors of each other. One's going this way, one's going that way. Okay? So when you have U plus the negative of U, you get the 0 vector. Just like we did in numbers, when you do 7 plus a negative 7, what do you wind up with? 0. Okay? Over here, what this is illustrating, if you take U, add to it the 0 vector, guess what you get? U. Because you're not adding anything to it, okay? In other words, the 0 vector is the additive identity vector, okay? Just like, give me a number. 1 plus 0 is 1, okay? 0 is the additive identity element as well. In the real number system, it's 0 vector is the additive identity vector in vector systems. Okay? So, let's see if we can see what this looks like. Let's go back to black. Oh man. And this is my, did I give you my sad little song before? I was, in addition to having worked on this for the last week and a half at least, you know, almost nonstop, not nonstop, but you know, last night I was here till after 9:15. So it was a very short night last night, and it's been a very long morning this morning. And in my differential equations class, I was making so many stupid errors right and left. Expect a bunch of stupid errors today. Okay, let's do, did I get back to black? I think I did. You tell me how to write U, 1, 4. Go.
1 to the right.
1 to the right. 4 up. Very good. So there's our vector U, which is 1, 4. Okay? And what's our vector V? The black vector V. 2 to the right and 2 down. Okay? So here is vector V, the black V, which is 2, negative 2. Now if you're adding those together, we've already done so, we know exactly what it is, but if you were to take U plus V, you would take V, move it up to the tip of U, and then from that point, go 2 to the right and down 2, and that's going to be the resultant vector, U plus V. And we claim that to be 3, 2, sure enough, 3 to the right, 2 up, that is indeed 3, 2. Or, if we had taken the vector V first, 2, negative 2, and then add to that 1, 4, that would be 1 to the right and 4 up. There you have it again. Same vector as we had before. So, take U, V and add to it U, or take U to it and add to it V. Either way, that represents the parallelogram method. Okay? Let's do the purple. And if this hits too crowded, I'll erase some of it. 3, negative 2, how do we do that?
3 to the right.
3 to the right and 2 down. This may get a little crowded. There's our purple vector U, which is 3, negative 2. And then what is our purple V? 3 to the left, up 2. And there is our purple V, which is negative 3, 2. And notice what happens. That forms a collinear, just going in opposite directions. So if you take this vector here and add to this one, guess what you are? At 0. Or if you take this vector here and add this to it, guess where you are? At 0. Okay? That's how you get to the 0 vector. I'm not going to draw the 0 vector for you. Okay? I did. There it is. Okay, never mind. Okay. You can't see it. It's not there. Okay? Or it is there. Whatever. Let's do the red sum. See how bad this becomes. How do we do 2, 1? Right 2 up 1. There we have it. This is our red U, which is 2, 1. And then I just drew the 0 vector. Okay? And what do we have when you add the 0 vector to that? You have the same thing. So nothing changes. There you have it. All right. In the book, they show, there it is in the origin. Okay. You can't see it. So there's one operation, adding 2 vectors. Let's go to a second one. Scalar multiplication. I think I'll clear the slide. Okay. Now I'll go back to black. Okay. Another basic operation is scalar multiplication. To multiply a vector v by a scalar c, we basically multiply every component in v by c. So in other words, c, a scalar c, a number, any number, okay, times a vector v would be, well, vector v is, of course, v1, v2 in 2 space, okay? So c would be c times v1, v2, which of course would be cv1, comma, cv2. It's sort of like you just distribute it across to each of the components, okay? Now, what does that mean? And by the way, C is called a scalar. In one sense, it scales the vector v. Imagine a vector v anywhere you want to imagine it there on the board. Okay? Give me a C, any C. Make up a number. 3. So what this would do, it would triple, say, if I should have had to give me a vector. Give me a vector. Name a vector.
2, 3.
2, 3. Okay? Vector 2, 3. That would be 2 to the right, 3 up. So let's call that our vector v. Okay? And if we scale that up by 3, the 2 is multiplied by 3, giving you 6. We're going to have problems here. Let's have c equal 2, okay? Okay. If you double this, you go to 4, and you double 3, and you go to 6. Well, what have you done? You've just scaled it upward. You have multiplied the entire vector by 2, because that's what you did. You doubled. You double the x value, you double the y value. Okay? Now, what do you notice? They're along the same line, just different lengths. What if we had, our c had been, rather than 2, had been 1/2? What would have been the new vector? 1 and 1.5. You're absolutely right. And where would that be? 1 would be right here, 1.5 would be right there. You would have taken half of that vector, which is exactly what you did. Still collinear, okay, but half the magnitude. Doubling it, still collinear, you double the magnitude. So that's what a scalar does. It extends it, whether it scales it up or scales it down. Okay? Now, sorry. Another thing, since I had to go downstairs and correct something, I didn't usually between classes I'll swap out books and I grab me a little something to eat and drink me a little bit of caffeine. This time I didn't get anything to eat and no caffeine, so I'm going, whoa, okay. Maybe I'll make it till noon. We'll see. All right. Now, let's talk about a special little scalar. And we actually have already talked about it, whether you realize it or not. What if the C was, well, I'll give you two of them. First, a C of 1. What would that do to vector V? It's the same thing. Well, guess what? 1 is the multiplicative identity element, just like 0 is the additive identity element. You multiply a vector by 1, you got the same vector. You add a vector to 0 vector, you've got the same vector. Okay? We call them the additive and multiplicative identity elements. But let's consider slightly different from that. What if your I would, or C was -1? What have you just done? If V was 2, 3, and C was -1, what would be your negative V?
Would you affect in the third part?
Yes, and it would be -2, -3, which would be right here. So this would be negative V, which is -2, -3. Okay? Which is exactly what we did on that last one. Remember when we had 2, -3, and 3, -3, 2? That was exactly the opposite. Still collinear, but now same magnitude, opposite direction. That's what multiplying by -1 does. So, multiplying by -2 would have done what? The minus changes direction, the 2 would have doubled the magnitude. Okay, so now I think that's crowded enough. Let's go to a new slide here. What do you reckon? And by the way, the opposite of V is the negative of V, and that would be negative V, right? So what do you think U plus a negative V would be? That's the definition for subtraction of two vectors. U minus V is simply adding the opposite of V to U, which is what we do in signed numbers, isn't it? When you're adding, or when you're subtracting signed numbers, keep the first, change the sign of the second one, and add them. Okay? That's how we do signed numbers. Yeah, I remember back in grammar school, subtraction was just 7 minus 3 is 4. You know, you did all your little tables and stuff. But when we got to signed numbers, it got to be make a lot more sense to say 7 minus and minus 3 is 7 plus the opposite of negative 3, which would be 10. So same thing here. For subtracting vectors, just add the opposite of the vector. And that's what you've got. So U minus V is the same as U plus a negative V. All right, so let's do, and guess what though? Guess what the easiest way to do? Think through changing signs and adding, or guess what? Doing it by components. But then you use sign number rule, which is the same thing. So let's do a few of these in example 3. Let V equal, vector V equal -2, 5, and vector u equal 3, 4. Okay? Find each of the following vectors. The A one asks for, what is 1/2 v? What do you reckon that would be? Yep. Second. -1, 2.5, or 5/2. Either one is perfectly fine. There's a 1/2 v. Perfect. What is, the B one says, u minus v. What would that be? Okay, you said what? Uh-oh. Okay. If necessary, write it out. 3, 4 minus a -2, 5. Okay? What would that be? Say again? Yes. Okay, I'm sorry. 5, -1. Perfect. I almost made an angle. I did make an angle bracket. I didn't mean to. Okay? What you do is 3 minus a -2, sign numbers. Okay? That'd be 3 plus 2 is 5. 4 minus 5. Again, the rule for sign numbers. Okay. Make sense? Okay. And let's do the C one is 1/2 v plus u. And what would that be? (1/2 v plus u). Anyone? Okay. All right. I'm not quite sure what you're doing.
You said -v plus u, sorry.
Yeah. Is what?
I didn't want to have u plus u.
Yeah, I was thinking that must be what you were doing. Okay. 1/2 v plus u. 2. 6.5. Now, did you do it the really lazy way? I thought so. Okay. Here's 1/2 v right here, and there's u right there. Add the components. Okay. 3 minus 1 is 2. 4 plus 2.5 is 6. All right. Or you could have written that 13/2. I don't care how you write it. But just write it right correctly. That's all I'm care. And in the book they did 13/2. Okay. I think they got it right in the book too, so I'm real proud of them. Okay. Good deal. Now let's go and list theorem 401. These are some properties of vectors addition and scalar multiplication in the plane. Plane meaning two-dimensional space. X, Y, whatever you want to call it. Just 2 dimensions in the plane. Okay? So here we're going to have let U, V, and W be vectors in the plane. That means they all have XY components. And let C and D be scalars. Okay, they don't have to be integers. They don't have to be fractions. They could be decimals. They could be rational numbers, irrational numbers, anything you want to be. Keep them real though. Don't have complex numbers. Okay. here are some of the properties of vector addition and scalar multiplication in the plane. First, u plus v, the sum of u and v, is also a vector in the plane. Okay? In other words, if u's in the plane and v's in the plane, when you add them together, you're still in the plane. You don't have anything pointing outside of the plane. You're all in the plane. Okay? And that makes sense. Now, that has a name for it. It's called the closure rule of addition. Okay? Or they say closure under addition or closed under addition. Okay? Meaning, if you got two vectors in a space, say the plane, they're both in the plane, when you add them, you can't create something outside the plane. You're still going to be in that one. Okay? Now, same thing applies to subtraction too, but we're calling this addition. Okay? Now, we've already done this one. What's u plus v? What's that the same as? V plus u, exactly. And that means that addition is commutative. Okay, or commutative property of addition. Now, a lot of these are just word closure, that means everything is within the same space. Okay, everything's closed, nothing's outside the space. Commutative. This is a dumb way to think of it, but this morning I drove from home to work. Okay? Even though I'm not going to do it, if I did go home this evening, the same route that I took coming in, I'm going to travel the same distance. Even though it was u plus v coming in and v plus u going back. Okay? They're the same. Okay? So that's how I think of it in my commute. It doesn't matter what direction I go, the distance is the same. I say that's not going to happen today because I've got to go to the Birmingham East Campus, and then I'm going home from there. I'm not going to come back here and then go home. No way. Okay, so it didn't work on my commute today, but it usually does. Okay? Now, number 3. Okay? It doesn't matter how you associate vectors. U plus v, and then you add to that w. That's the same as taking u and adding to that the sum of v plus w. Now, and this means addition is associative. Okay? It's associative. It doesn't matter what order or grouping that you do of adding vectors, it comes out the same. Now, this is one place where that parallelogram method maybe does help. It doesn't matter if you add this vector to this vector to this vector to this vector or this vector. Yeah. If you're adding the same ones, they're all going to wind up at the same place. Okay? It doesn't matter if you add these two first and then add this one, or add this one to the sum of these two. It's going to wind up the same place. Especially if you think of your component. U1 plus U1, U2 plus U2, V1, V2, and then add W1, W2. Add these two first. It's U1 plus V1, comma, U2 plus V2. Add to that W1, W2. So U1 plus V1 plus W1, comma, U2 plus V2 plus W2. The same thing you get here. It's just that you're adding these two first. U1 plus V1 plus W1. That's still U1 plus V1 plus W1. And U2 plus V2 comma plus W2. Guess what? U2 plus V2 is going to be the same either way. So actually, I think component notation makes that even clearer. Okay? Now, we've already hit this one. Talked about it anyway. What is U plus the 0 vector? That's going to be U, okay? And that's called the additive identity element. Additive identity element. They call it element here, property. Additive identity property. Okay? And we've already done this one, or at least illustrated it. Okay? If you take U and add to it negative U, what do you get? The zero vector, exactly. And that's the additive inverse. Okay, property. That if you add the opposite of something to something, you will end up with zero. Okay? Number 6. So the first 5 are basically addition things. The next 5 are mostly multiplication, though they have some addition components in it. C times U, remember U is in the plane. You multiply it by a scalar, CU is also in the plane. And that looks a lot like this, that U plus V is a vector in the plane. So now we say that scalar multiplication is closed. In other words, closure of scalar multiplication, under scalar multiplication, I don't know why they say under, but scalar multiplication is closed. You start with a vector in the plane, multiply it by any constant. The new vector is going to be in the plane too, so you're in the same place you began. All right, number 7. I can't write. Okay, there we go. Number 7. Now here is a okay thing. C times U plus V is equal to CU plus CV. Okay, what do you reckon that is? That's distributive property. Now, they just say distributive property, okay? That's all they say. I like to say distributive property of scalar multiplication over vector addition. That's a lot wordier, but hopefully you see what I mean. You can either add the two vectors together, then scale them up, or scale them first and then add them up. You're going to get the same thing. So it's the scalar distribution of scalar, distributive property of scalar multiplication over vector addition. Okay? Now number 8 seems a little related, but it's not quite the same. C plus D times U, is it? Yeah, U. That's the same as, you tell me. Oops, I forgot my arrow. CU plus DU. Okay. All right. Well, that's also a distributive property, but I say this is a distributive property of vector multiplication over scalar addition. Okay. Now, you don't have to add all those words, but to me, just to call them both distributive properties, they are, but they're a little bit different. Okay. Now, notice what we've left out. You can't have a vector on the outside and the sum of two vectors on the inside. We don't even know what vector multiplication is. So we're not going to say it, and we can't say it. Okay? Of course, if this was a number here, that's just a regular distributive property. So I just want that. Okay? So you can only add vectors and multiply a vector by a scalar. We know later, we'll find out how to multiply vectors together, but that's not going to be important for this course. We're only going to add vectors to vector, and multiply a scalar by a vector. Okay, number 9, I'm running out of room very fast, is C times du is the same as, you tell me. CD times U. Okay? Now, that's a bit, maybe a little strange, but bizarre, but it's okay. If you have a scalar multiplied by a scalar times a vector, it's the same as taking two scalars, multiplying them together, and multiplying that by the vector. It is a form of an associative property, just like this was associative, okay? So it's the associative property of two scalars and a vector. Let me put it that way. Two scalars and a vector. Okay. Now, that's probably good. And again, I want you to notice, what are we missing here? We're missing vector multiplication. We have not defined vector multiplication. In fact, I'm trying to think in this course if we'll ever define vector multiplication. You can multiply a vector by a scalar, but so far we do not have the tools to multiply vectors by vectors. It can be done, but there are very stringent restrictions on it. Okay? And then the last, the one that we've been dreading, okay, is, and this is pretty simple, we've already done it, 1 times the vector u is going to equal what? U. Why not? You? Me? Who? No, okay. And this is the multiplicative identity element. They just call it multiplicative identity property. They call them all properties, which is fine. Okay, we had already done that. Okay, now they do a little proof here. I'm sorry, for one or two of them, okay? But if you like doing the proofs, want to do the proof, please do. We just have very little time in the term left, so let's move on. Now, so far we've been talking about vectors in a plane. But guess what? You can have vectors, okay. A vector is a line segment, directed line segment. So you can, I mean, by definition, a vector is a one-dimensional entity, okay? You can put it in a two-dimensional plane, but it itself is just a one-dimensional entity. Now you can also take it into space. I like to use this corner here, that'd be my x-axis, that's my y-axis, this is a z-axis, so I can do a vector with so far on x, so far on y, and so far up. That might put me up here, a vector from the origin to here. That would have x component, a y component, and a z component. You can do there. I can picture that kind of. I can't draw it on a two-dimensional board worth a hoot, but I can picture it, okay? But you can do vectors in space. As big as you want n to be. It has to be finite, it can't be infinite. But it can be 7 space. I just can't illustrate it for you because we live in 3 space, okay? You can't do a 7 space. You can go back and look at a plane, 2 space, or you can look at a line, 1 space, 1-dimensional space, but I can't begin to show you 7 space. But vectors can be in what they call Rn, where n is any integer, okay, positive integer, okay? So, another deal with vectors, and we've already hinted at it and done it, but maybe not specifically said it. Vectors can be represented by ordered entities. Okay? Now what do I mean by that? In the plane, they're ordered pairs. That order in which those number appears makes a difference. 2, 3 is different from 3, 2. Same two numbers, but they're different in the plane. One is 3 to the right and 2 up. The other is 2 to the right and 3 up. Different vectors. Okay? So they are represented by ordered pairs on the plane. On a straight line, just a single number. In fact, straight line is the number line. Okay? One-dimensional space. 0, 1, 2, 3, 4, negative 1, 2, 3, 4, you know. That's a number line. It's just represented by a single number. 17, negative 4/3, you know, whatever, you know. Each of those are numbers on the number line. Each ordered pair represents a vector, you might say, in 2 space. An ordered triplet would be that point we were talking about before, where you had an x, a y, and a z. That would be this point out here. Okay? When you get to the higher ones, you just keep on trucking, but you just can't visualize it. Okay? Then you talk about it being an ordered n-tuple. Okay? Single, pair, triplet, and after that we get into n-tuples. Just like 3 babies would be triplets, 4 babies would be quadruples. Okay? You know, quadtuplets, quintuples. Okay? All right, that's 5. Okay. So an ordered n-tuple represents a vector in n space, whatever the n happens to be, 1, 2, 3, 4, 5, whatever. For instance, ordered triple has a form of x1, x2, x3. An ordered quadruple would be x1, x2, x3, x4. And in general, an ordered n-tuple would be x of 1, x of 2, x of 3, x of 4, dot, 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 up to x of n. N-tuples. Set of all n-tuples is called n space and is denoted by r superscript n. So R1 would be one space along a line, R2 would be in a plane, R3 would be in space, and Rn would be in dimensions, which we can't see or imagine. I can't anyway. An n-tuple would be x of 1, x of 2, x of 3, x of 4, up to x of n. Can be viewed as a point in Rn with is that an I or a J? I think it is. With x of i's as the coordinates of the vector. Okay, that's what the x of 1, x of 2, x of 3, up to x of n. X of I would be a coordinate. Any coordinate in there. And then if you had that kind of a space, n space, then a vector in n space would have n components, just like what we're talking about. Okay. Now, the sum of two vectors in Rn and a scalar multiple of vector Rn are called the standard operations and are defined as follows. So this takes what we were saying about 2 space, brings it up to n space. So let's let U be a vector in n space. That means you have a U1, a U2, a U3, a dot, 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 up to and including U sub n. Okay? That's a vector in n space because it has n components. Each one of those subscripts is counting off, numbering which component it is. Okay? Now, let's let V also be a vector in n space. So it has a V1, a V2, a V3, and a dot, dot, dot up to V sub n. All right? Goodness gracious, I'm getting almost dizzy feeling. I think I'm missing my caffeine. Okay, so it's also in n space, same dimension, so it's in the same space. Now, these are both vectors, and I'm going to use this symbol as an element of R sub n, because this has n components, this has n components, that's in n space, R sub n, R superscript n. Now, I sort of skipped something. I should have said this first. These two vectors, to talk about their equality or not, okay? For those two vectors to be equal, they've got to be in the same space. You can't say a vector in R2 can be equal to a vector in R3, because this one has 3 components, that one has 2. How in the world could they be? They could. Because U sub 1 could equal V1, and U2 could be V2, but this has a U3, and this one doesn't. V doesn't have a third. You can't do it. So for these to be equal, every one of the components must be identical, and it has the same number. Okay? So they have to be in the same space. Okay. Should have said that first. Now, and then I think I did say this one. Your standard operations in space, or R sub n, or superscript n, would be your vector addition. You can only add 2 vectors if they have the same number of components. So they've got to be in the same space as well. Okay? And if you multiply one of these vectors by a scalar c, that's also going to be in space, because you just multiply this by c, that by c, that by c, every one of those by c, including that. And then you have scalar multiplication. Okay? Don't ever leave off a dimension. Okay. So with those two things said, these are vectors in Rn, and c is a real number. Okay. Then the sum of u and v, u plus v, is simply going to be, and this is what I was saying before, u1 plus v1, comma, u2 plus v2, comma, u3 plus v3, comma, dot, 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 all the way up to and including u sub n plus v sub n. Okay. All right. That's the sum vector. All right. The scalar multiple of u by c, cu, would then be simply cu1, comma, cu2, comma, cu3, comma, dot, 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 up to and including cu sub n. Okay. Now, as in 2 space, the negative of u minus u would simply be minus u1, comma, minus u2, comma, minus u3, comma, dot, 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 all the way up to and including minus un. Now, I guess that's all that needs to be said about that. I was thinking there might be something else. And now we can talk about, we talked about adding the two. U minus v would then be the same as u plus the opposite of v, which would be, however you write it, is going to be u1 minus v1, comma, u2 minus v2, comma, u3 minus v. Goodness gracious. My things are dancing in front of my eyes. It's just sort of crazy, comma, dot, 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 comma, u sub n minus v sub n. Okay. And of course, the zero vector in space. Okay? It's not the same as a zero vector here, or the number 0. Okay? It has to be 0, comma 0, comma 0, comma dot dot dot, up to and including 0 n zeros. Okay, it has to have n components to be an Rn, and each of those has to be a 0. All right. I hate to do this because we got started late, but I need to go splash some water on my face or something because my eyes are just kind of driving me nuts. So why don't you all take advantage and just take a little. Of course, I couldn't go out down the hall without a dozen things flowing through my brain about, oh yeah, I had to stop and talk with Dr. Thomas for a moment about some of it. And I got some bad news from her, but I'm not going to worry about that anymore, as I can't do a thing about it. Let's do example 4, bottom of page 149. Okay. Let's let U equal -1, 0, 1. What can you tell me about U right now, just given that information? What kind of space is it in? It's three-dimensional space. It's in R3, R superscript 3, R to the third, or sometimes called 3 space. Okay? I can't write. That's a 2, -1, 5. I'm talking about 3 space, so when I went to write 2, I wrote a 3. Okay. These are both in R3. Okay, R cubed, you might say. Find each of the following. A, what is U plus V? Really tough stuff here. What is it? 1, -1, 6. Perfect. Okay. The B part. What is to you? As in happy birthday. No. What is that? -2, 0, 2. Perfect. I want to write an angle bracket, but I'm trying not to. C. What is V minus 2U? Guess I take a little more thought. If you need to write more things down, do it. See what you get. Okay. Is that a minus or a plus? V minus 2U. That'd be 2 minus 2 times -1. Second? Right.
So
4. Okay. Next. -1. Perfect. Next.
7.
That's a positive up there. 5 minus 2 times 1. 3. All right, that's 3. Good. Okay. Make sure they got it in the book right, too. 1, -1, 6. 2, -2, 0, 2. And 4, -1, 3. Perfect. And guess what? All of those are in R3. Gotta be. You can't do them without it. So, properties of vector addition and scalar multiplication in Rn. Guess what? They're the same as R2, okay, that we were doing before. So I don't feel like writing them down. If you got them, you already got them. Your addition is closed under vector addition is closed to. Vector addition is closed in Rn. The community property works in Rn. Associative property of addition works in Rn. There is an additive identity element. Now this is not quite the same as in R2. It looks the same, but it's a different zero vector. The zero vector in Rn has n zeros, okay, not 2, okay? And u plus the negative u, the opposite of u, is going to be the zero vector in Rn, additive inverse property, additive identity property, and inverse property. Cu is a vector in Rn, that means scalar multiplication is closed in Rn. You can do those same two types of distributive laws. So C times U plus V in Rn is the same as Cu plus Cv in Rn. And C plus D times U in Rn is Cu plus D. And if you're really careful about it, you can associate multiplication as long as you have two scalars and one vector. That works fine. C times du is the same as Cd times u. And then the last one, the multiplication identity element, is 1 times u is just u. Now, here's a little blurb on the side of William Rowan Hamilton. He looks like he's a bright guy, doesn't he? I mean, it looks like he is intense. Of course, he almost looks a little bit like the guy on MASH, but no, never mind. That's beside the point. Okay, considered to be Ireland's most famous mathematician, and he did an incredible amount of very important work. Some of it way beyond his time. In quantum mechanics, we talk about something called a Hamiltonian. And I don't know any other Hamilton that it could be named for except him. And he was back in 1865, was the year he died. No one had even thought of quantum mechanics before, much less heard of it. And yet some of the math that he did in his lifetime was applicable to quantum mechanics. If indeed that's the same Hamilton, I think it is. Okay. So let's do example 5, which uses some of those properties. And this time we're going to do them in R4 rather than R3. So let's clear our slide here and do here. Here is vector u in R4. 2, negative 1, 5, 0. Okay, here's vector v in R4. 4, 3, 1, negative 1. And have we got another one? Yeah, here's good old vector w in R4. It's negative 6, 2, 0, 3. Okay. They're all vectors in R4. Of course they are. They have 4 dimensions, 4 components. Okay. It says find x using each equation. Whoa. Okay. Here's an equation. A. X is equal to 2u minus parentheses v plus 3w. Okay, how are we going to do that? One step at a time. Let's start by writing 2 times vector u, and vector u is 2, negative 1, 5, 0. Minus, and we'll do what they do first. V is 4, 3, 1, negative 1, plus 3 times negative 6, 2, 0, 3. And let's basically use the rule of order of operations. Okay? So where would you begin? Do the math. 4, -2, 10, 0, minus. Now let's not do, you decide how much to do in one bite or chunk at a time. You want to get that whole parenthetical expression, or you want to do in 2 pieces? I don't care. 2 pieces, okay? Then I'm going to write down the first one. 4, 3, 1, -1, plus, and give me the next piece. -18, 6, 0, 9. Okay? I can't do much else with this, so I'm going to write it down. 4, -2, 10, 0, minus. Can we do this at once? What do we have here? That's a minus 18, there's a 4. Yeah. -14, comma, 9, comma, 1, comma, second, 8. Good. And then I think we can do that last step at once. And what's that? Ooh. Maybe not. You want to do that twice? Okay. Yeah, it's 4 minus a minus 18, 14, which would be 18. -11.
Is that a 10 on the left?
That's a 10 on the left and a 1 over there. 9. -8. Perfect. Oh, let's see if they got it right too. 18, -11, 9, -8. Yes. Okay. Take as many steps as you need. You know, don't rush things. It only opens yourself up for really problems. Okay. Now, if you thought that was interesting, let's try this one. The B part. Oh, yuck. I should have erased just the A part. I erased the whole thing. So I've got to go back and put U equal 2 -150. This lack of sleep does not make for good performance. 4, 3, 1, -1. W equal -6203. All right. The B part says 3 times x plus w, and by the way, that last vector we had was the vector x, okay, is equal to 2u minus v plus x. Uh-oh. SpaghettiOs. What in the world are we going to do with this? What would be your recommendation?
Treat it like an equation.
That's exactly what I would do. And how do you mean that?
Multiply, combine, like terms.
Okay. Tell me what to do then.
On the left will be 3x vector.
3x, is that what you said?
Mm-hmm.
Okay. Continue. Plus 3w, is that what you said?
Mm-hmm.
Okay, is equal to 2u minus v plus x. Now what?
You want to make it equal 0? Combine like terms?
Not quite. Okay. What does it say to do? Find x using each equation. We want to find out what the x is. We know what u is. We know what v is. You know what w is. We don't know what x is. That's what we're looking for. So guess what we're going to do?
Solve for x.
Yes, solve for x. Get all the x's on one side and everything without x's on the other side. So what do we do first? Subtracting x from both sides. Now, do you want to go on and do the other part too, or wait on that one?
Yeah, 2x.
Okay, let's go. This will be 2x plus 3w is equal to 2u, if I can read my writing, minus v, and that goes to 0. Okay? Now what? Second? Yeah, that's a u, that's a w. So what will you do next? Subtract 3w from both sides. And that gives you, this goes to 0, 2x is equal to 2u minus v minus 3w. Okay? And one last thing. All right, then take that, divide both sides by 2. Okay? Now I'm going to write it slightly differently, okay? And write this as x is equal to 2u divided by 2 is just u minus 1/2 v minus 3/2 w. I think that'll be easier computationally. So let's now plug in what that is. This is 2 minus 1, 50, minus 1/2 of 4, 3, 1, negative 1, minus 3/2, that's an ugly 3, isn't it, of negative 6, 2, 0, 3. All right. Good. It's going to be a 2, negative 1, 50. And you do the next part for me. Two, 3/2, 1/2, negative 1/2. Okay. Next. Okay. Okay. If you made that a 9, I'm going to make that a plus set. Okay. And that would be 9. Negative 3. 0. It's a 3 there, yes. Negative 9/2. Wait, okay. Yeah, negative 9/2. All right. Now, since you did that, I'm going to do this. I'm going to make this a plus with a minus there, minus there, minus there, and plus there. Is that okay? That'll make it a little easier to do, I think. And what will this give you? Just looking at this, 2 minus 2 is going to be 0. So your first component here is going to be 9. Okay. I don't think anything else is going to work that nicely. But let's do a minus 1 and a minus 3 is minus 4. Minus 3/2. Well, 4 would be 8/2 minus 3/2 would be 5/2. Is that right?
Yes.
Yeah. Okay. So we got those done. Okay. Next, that's a 5, not a 50. 5 minus 1/2, that would be 10 halves minus 1 halves would be 9 halves, because that's a 0, so those are done. Okay, and then finally, negative what?
Negative 8 halves.
Which is?
4.
4, negative 4. Okay, let's see how they did. 9, negative 11 halves. Whoa! 9 halves and negative 4. Okay. We have a problem here, Houston. Let's see if we can figure out what it was. Yuck. Okay, it's only that third component, so let's make sure we got them all right. And obviously the other things are right. So we have a 5. Okay, a 5, a negative 1/2, and a 0. Now maybe I missed a sign here. Let's see.
Is it the third component or the second component?
It's the third component. Oh no, you're right. It's the second component. I'm sorry. Okay, let's look at the right one here. Okay, 2 negative and okay. If you understood that, you've got problems. Okay, and I think my signs must be right. So let's see. Let's say minus 1, a minus 3 halves, and a minus 3. Okay. And minus 1 and minus 3 is minus 4, which would be minus 8 halves minus 3 halves, and I subtracted rather than add. That's minus 8 halves minus 3 halves is minus 11 halves. Right? And it's a minus. Yes. Okay. Don't get carried away. Don't move too fast. Make sure you can follow. Okay. There's several ways you could approach that. That was one way. Okay. I think it worked pretty well. Except for the error. We are. Oh man. Just when we're beginning to have fun, huh? We're always having fun. Okay. So we'll begin next time with Theorem 4.3 at the top of the following page.
So
Okay.
when is our test 3 due?
Say this one more time.
When is test 3 due?
Okay, the test one. Oh, that was the thing. Okay, what was your question?
Yeah, about the test.
Okay. Here. Y'all should have stopped me a few minutes earlier, but let's hit it now. Okay. Now, research papers are due Thursday. I'll take them before Thursday. Please get them to me by Thursday. Anything after Thursday, you start losing points. Okay? First test, I've returned all those to you, right? I asked that earlier. Second test, I'm still missing 3, or maybe I just haven't graded them. Okay? So as soon as I get those graded and I get them all, I'll get them back to you. Okay? Third test, I think you still have, because you just recently got, and so, Mark Travis absent, Audrey absent, and Julia absent. Okay, so, get your test 3 in by Thursday too, if possible. You don't lose points on that, but please don't have that out at the same time your last test, okay? So get that in by Thursday too. I will return everything that has been turned in to me, except the research papers, of course, because I have to keep those for samples of student writing. I'll return all the tests that have been turned in to me by then. I'll return them to you so you can have those. I don't want to carry them around. Okay. I will also, at the end of class, give you your last test. It's the final exam, but it's not comprehensive. It's just the last test. meaning final exam. Okay, so I'll give you that. Now, when is that due? Well, technically final exams are Tuesday, Wednesday, Thursday of the following week. I'll accept them any one of those days. In fact, if you finish it by Monday, if you finish it over the weekend and want to turn it in Monday, I'll take it. So let me give you my schedule. Monday is a class day. So I'll be here teaching from 8 in the morning until 10:40. And I have a short 20-minute break, and then I'm here again from 11 until 1:40. After 1:40, I usually am still up here for a while, but basically 2 o'clock until 6 o'clock, I'll be down in my office. You can turn anything into me anytime. If I'm teaching when you come to bring it, slide it under my door. You know where my room is, 265, my office. Everybody know or not? Okay, you do know. Everybody knows? Okay, we'll do that. This morning's class, not everybody seems certain about it, so I get that. Okay. So if you can't find me, just slide it under my door. Okay. Now, Tuesday, I'm here 7:45 in the morning, and I'll be in my office pretty much until about noon. At noon, I have a test in this room, a final exam that probably is going to go, it probably won't be 2 hours, but I'm allowing 2 hours, 12 to 2. Okay? Then after 2 o'clock, I'll be back in my office until 3:30. At 3:30, I've got to go to the Birmingham East Campus in the Ethel Hall Health Professions Building, and I'll be there from 4 to 6, Tuesday and Thursday. Okay, that's Tuesday. Wednesday, I'm in my office basically 7:45 in the morning till 6 in the evening. Wednesday, all day long there. Turn it in anytime there. Thursday, no finals, so I'll be in my office 7:45 in the morning until 3:30. 3:30, I go back to the Birmingham East Campus, and by the way, it's room 103 in that building, and I'll be there from 4 to 6. Okay, and then here's the deal, folks. I'm not absolutely certain whether the college is open that following Friday or not. All summer, June and July, we've been closed on Fridays to say, we've been working 10-hour days. I don't know about the first Friday in August. It's not June or July, but they may be giving us that Friday off too because we're working 10-hour days Monday through Thursday. But I don't know that for a fact. Whether we're working or not, I'm not. I've got a treatment that Friday. I've got to be at the clinic at 7 o'clock for blood work, 8 o'clock for the treatment, and it takes pretty much all day, and even if it doesn't take all day, I'm not good to drive very far, so I drive home and usually go to bed, okay? It's not bad, it's just they give you Benadryl and that kind of stuff, and I just get really sleepy with that. So I shouldn't be driving very far with that, so I'm not coming back to campus. So if the college is open and you need to turn in something Friday, you can slide it under my door. I'm not sure the college is open. I don't think it will be, but if it is, you can slide it on my door. That way, when I get back in Monday morning, it'll be there. I can grade it. Grades are due in for us. We have to have them in by noon on Monday. So please, I've got to have, I can't take anything at 11:30. I just can't get it graded, averaged, and everything in. You'll get it incomplete. But as soon as you get me the stuff, I'll change the I to a whatever grade it is. So you can do that if you want to, but I'd rather you not. Okay. Because then, after next Monday, I'm not on campus again until registration for fall. So if you give me something late, it's going to be late getting changed the I. And if you have to have something fall term at your school, you're not going to have it. Okay. So anyway. All right. That's pretty much where I'll be, what I'll be doing. I'll be grading like crazy from this afternoon after my class is over at 3:30. At 5:30 till 6. I'll get as much graded as I can. That won't be a lot. And then tomorrow, I'm in class until, like I said, until around 2. From 2 to 6, I'll be grading like crazy. I'll try to grade some tonight. I'll try to grade over the weekend. But I need to have everything of yours graded by Thursday morning because I want to give it all back to you. So I'll be crazy grading today and tomorrow until.
But you won't get points taken off if you turn in test 3 sometime next week.
Oh no, yeah. Test you don't lose points. It's only the paper. But test 3, get it in as soon as you can. Okay. All right. Any other questions?
We're meeting here Thursday, correct? Thursday.
Yeah, Thursday. Yeah, this Thursday, day after tomorrow, we're here and we get as far as we can in chapter 4. And see, I have to have the test made out beforehand, so the odds are it's going to have more questions than what we covered because I don't know where to stop it. And I'll just make those optional questions. Or you can leave them blank or optional. They won't count off. So we'll get as far as we can Thursday, and then I'll give you your test, and you get it back to me as soon as you can. All right, good deal. Been a great class. Well, we'll see you Thursday. All right. We won't get into that yet, how good you are. Okay.